मराठी विज्ञान परिषदेनं यंदापासून सुरू केलेला जीवनगौरव पुरस्कार यावर्षी प्राध्यापक जयंत नारळीकर पुरस्कार डॉक्टर सोमुख रे चौधरी यांना आज सकाळी आपल्या सर्वांच्या उपस्थितीत प्रदान करण्यात आला. मी डॉक्टर सोमुखराव चौधरी यांना मंचावर आमंत्रित करतो. ते खगोल आणि भौतिकी शास्त्रज्ञ आहेत आणि सांगायला मला अतिशय आनंद होतो, हरियाणाच्या अशोका विद्यापीठाचे ते कुलगुरू आहेत. एवढे एक महान व्यक्तिमत्व आज आपल्यामध्ये उपस्थित आहे. त्यांच्याकडनं जेवढे ज्ञानकण आपल्याला गोळा करता येतील तेवढे घेऊन आपल्या विज्ञान संपुटात आपण साठवून ठेवूयात. सर, थँक्यू.
Thank you very much. I apologize at the beginning. I'm going to talk in English, even though I understand Marathi and I've lived in Maharashtra for such a long time. I'm not confident giving a whole scientific talk in Marathi. So please bear with me. It is a really great honor for me to be here. Not only because this is an occasion organized by the Marathi Vigyan Parishad, but also that I was given an award today, and this lecture is in honor of Professor Jayant Narlikar, who has been my absolutely, thank you very much. Professor Jayant Narlikar has been my mentor in my professional life. I came into science and astronomy reading his books. In school I read his books and thus got interested in science and in astronomy, structure of the universe, and all his Cambridge University Press books. Then when I went to study in Cambridge, I did my PhD, same place where he did his PhD at the Institute of Astronomy, University of Cambridge, where I studied his books again. And so, and then I came to Pune in 95 to work at his new institute in Ayuka. And since then, from 95, he put me in charge of the science outreach and school programs at Ayuka in Pune. And I've worked with him since then. We built a whole program involving 400 schools and their teachers. We built a science park 30 years ago. You heard about a science park this morning. I built a whole science park in Pune together with Professor Narlikar. So I've actually worked quite a lot with hundreds and hundreds of school children together, addressing them, answering their questions, and in Pune, away from Pune, and for the off and on for the last 30 years. So getting a prize in his honor is really, I cannot imagine anything better. I give him, on behalf of the Astronomical Society of India, 7 years ago, I presented him with a Lifetime Achievement Award. And in this picture you can see that I was giving him this award on behalf of ASI. And he told me in his characteristic humor, "My name is Narlikar, why are you giving me a coconut?" So this kind of underlines the humor. One of the things that scientists lack in general is a sense of humor when they're talking about science. And this is one of the reasons science does not come across to the general public as much as it should. So sense of humor is very important, and this is one of the things that this man actually has underscored in everything. Every encounter you have with Professor Jayant Narlikar, you will find that whatever he says is underlined with a sense of humor. And of course, we all know that Maharashtrians in general, the sense of humor is very important. So getting across very much the science to the people is important. Anyway, having said that, as I said, I'm very proud that the Achievement Award is named after Jayant Narlikar. I move on to a very topical thing. I named this talk why we are going to space to see the sky. And you would think that's a very strange thing to say. To us, if you look at the sky, it's space. But traditionally, when people looked at the sky before they knew what the stars were, what did they think? The sky, to many people, is the limit. Many people think that as you look at the sky is some kind of a firmament, some kind of a limit beyond which nothing exists. And the stars are in the sky. But as we learned more and more about the universe, we learned that the sky is not the space. And the relation between space and sky has been there. There's a confusion in there from the very beginning. If you look at even our scriptures, if you look at traditional Indian astronomy, even going through Aryabhatta's time, as well as Bhaskara and people like that later on, there is a constant debate about space and the sky. And so when we come to, so what I'm going to try to do today is to make a distinction between space and sky, and why to an astronomer like me now, right now in 2023, space is very important in terms of going to the sky. Now it's been all the papers, you've heard about ISRO's achievements with Chandrayaan, and then Aditya studying the sun, and this, if many people haven't seen, is from yesterday. The first images of the sun from Aditya. Please applaud this. Aditya has not even reached the Lagrangian point that it's supposed to reach on the 7th of January. It is on the way. It was launched, as you know, in early September, and it is going to 1% of the distance between the Earth and the Sun, and it is going to study the Sun all day long for 5.5 years. It has two big instruments. One of them was built by my team in IUCAA. When I was IUCAA director, we handed it over to ISRO before I left IUCAA. And this is the SUIT instrument, which is the instrument that is now being turned on as the spacecraft is moving. And the front hatch has been opened, and we are testing things. And these are the test images. And this is the first time from space the whole sun's picture has been taken by any instrument. There are NASA instruments out there, there are ESA instruments out there, and what they have done, their field of view is very small. What they do is they can take pictures of small parts of the sun, and they put them all together into a mosaic and publish it. We have built an instrument in which every shot will have the whole sun in it. Why is it special? I will show you in a moment why is it special, and this is why I want to tell you why Aditya had to go to space to study the sun. Why can't we do it from the Earth? So to us, you look at the sky and you see the stars, right? But the stars as we see, these are the stars you see with our eyes. Not the most common Van Gogh painting, but we see these things in the sky, and we see them because our eyes can see them, but we have to make sure we understand that our eyes are very limited. Our eyes can only see a very small part of the energy that celestial objects like stars, galaxies, planets can emit. And for the entire history of mankind, no matter what language you speak, no matter what part of the world you are in, we have only concentrated on what we can see, of course. Only in the last century have we started to build instruments to see beyond what our eyes can see. Right, we have to understand that, and this is why astrophysics is a new subject. Astronomy has been a very old subject. We have started to understand that there's a lot more to learn, because each of the things out there, those stars in there, are emitting different kinds of light. We say light because our eyes can see it. But what about the other kinds of light that our eyes cannot see? There's a lot of information in there. So this is what I mean. A lot of you know that we have the whole electromagnetic spectrum. Light is emitted by disturbances in electrical and magnetic fields, and it produces a little light in a small range of wavelengths, which is in here. In this entire range of electromagnetic spectrum, you have gamma rays, you have X-rays, you have ultraviolet rays, you have the light that our eyes see, visible light, you have infrared, you have radio waves, microwaves. They're all the same thing. They only differ in energy or frequency or wavelength. Wavelength and frequency are connected with each other. High wavelength means small frequency, etc., and small energy. And this visible light, our blue to red, everything fits in this tiny thing, and this is on a log scale. So there's so much energy in form of electromagnetic radiation that is coming to us, and for the entire history of mankind, we've seen only that tiny thing, right? And our entire knowledge about the universe is based on only that tiny bit. So when you say 2,000 years ago, somebody worked out, they knew about the sky and the universe, remember, they did not know anything outside that little speck, that little bit. All of this does not only, cannot be seen by the human eye, it does not come through the atmosphere. And I'm going to tell you why. What you can ask me, what can we learn going out of that visible part? What can we learn? Why are we sending Aditya to space? This is what the sun looks like in those different parts of the spectrum. So here's visual. Visual means our eye. The sun looks boring. You try to look at the sun through even all those solar glasses, etc. What do you see? It's just a disk. And sometimes you have spots. But look at what it looks like in the ultraviolet. That's what the sun is. Look at what it looks like in the X-rays. Our eyes can't see it. And the ultraviolet and X-rays don't come through our air. So you have to go to space. And this is why before 1960, we did not know what the sun looks like. Because we had not gone to space. The ozone layer stops all ultraviolet radiation. That's why we don't get skin cancer. But it also means we are prevented from seeing the sun. Right? This is what the sun looks like in the infrared. So as soon as your eyes get opened up to the different forms of radiation outside the visible range, you know what astronomy can do. The whole power of astronomy has been unleashed. It is a new subject. The people who are young in this auditorium are the people who are going to do real astronomy. We've only started. We've just scratched the surface. And that is because we are understanding the universe in a very different way. Not just the sun. Look at what galaxies look like. Here's a galaxy. Same galaxy, same scale. That's what it looks like in a normal optical picture that you take with your camera through a telescope. But look at what it looks like in the X-rays, look at what it looks like in the infrared, look at what it looks like in the radio. These are very, very different pictures. Each one of them tells you a different story about the same thing. Look at the M81 galaxy. This is the same galaxy. In X-rays looks like that, and in radio looks like that. Each picture gives you a different story. And this is where I want to characterize what an astronomer is. What is an astronomer? I am a very, very special kind of scientist. I cannot go into a lab and touch my subjects. If you're a biologist working on snails, you can prod your snails. If your snail dies, you get another snail and you can repeat your experiment. I cannot go to the star I study. I cannot repeat that experiment because I can't repeat that star. Right? So, very special kind of science I have to do. First of all, I cannot repeat the experiment. And secondly, I get very little information. I get information in the form of some light that comes to me. And now, that information is increased because now I've discovered that there are radio waves coming and ultraviolet coming, etc. So 5-6 different kinds of information is coming. So I would think my position as an astronomer is like a detective who's appeared at a murder scene 2 months after the murder. Everything has been washed up. There is some stain on the wall maybe. People have half forgotten what happened, and I'm interviewing people. And from that I have to make up a story. That is the challenge, and that is the romance of astronomy. To me, that is wonderful, because I have to make up a story, has to be accurate, from very little evidence, very little information, and this is why astronomy needs a whole range of subjects. We need engineers of all kinds, we need chemists, we need physicists, we need mathematicians. Everybody comes together in a very interdisciplinary way. Everybody gives us our skill, and with the limited data, we get stuff out. And what kind of stories do we build? We build stories like this, which you have known. You know that this whole famous way of looking at the, the elephant and the blind people. Somebody looked at the foot of the leg of the elephant and said, oh, the elephant, it must be like a thamba. And then somebody looks at the tail of the elephant, he said, elephant must look like a rassi. And then somebody would look like, etc., etc. So we have to put together the leg and the tail and the ear and the trunk of the elephant to find what the elephant is. And these are the different kinds of information I need from the different parts of the electromagnetic spectrum. The gamma ray tells us something else, the X-ray tells us something else, the radio tells us something else, tells us what the tail is like of the elephant. Then the astronomer gets the story like a detective, and thus. And this is why I would tell you that this is why space astronomy is very important. I'll give you one example of what this kind of, I'll just skip this. Here is why. Here, I don't know whether you can see this, but it tells you on the y-axis in this graph is transparency. And on the x-axis is what kind of radiation it is. It shows you that in the optical part, which our eye is, the atmosphere is transparent. And in the radio part, where the very low energy, long wavelength radiation, the atmosphere is transparent. Everything else is blocked by the atmosphere. Now I want you to understand and tell me, isn't this a coincidence that our eye sees only that part of the radiation which the atmosphere is transparent to? Think of what would happen if our eyes were sensitive to somewhere there. There are rattlesnakes, kinds of snakes that can only see infrared. Snakes cannot become astronomers, right? They don't see the sky. They don't see the stars. If we were only sensitive to the ultraviolet, that ultraviolet light doesn't come through the atmosphere. We would not know there are stars out there. So that is a very interesting coincidence you have to think about. And we are blessed because we have thousands of years of tradition of astronomy, studying astronomy, mathematics, everything, because we see the sky. But if we want to play the detective and put all of this information together to find out what these things really are, we need that whole thing, and this is why we need to go to space. We have to go above the atmosphere, because the atmosphere absorbs all of this radiation. So I'll give you a couple of examples of how going to space is helping us do that. And a lot of people come to me and say, look, why is ISRO spending so much money? Actually, it's not that much money. Sending something to Chandrayaan and then, you going to study the sun. You won't see the sun from the earth. Most of the sun's fun things are happening in the ultraviolet and X-rays. And you have to go to space for that. This is why Aditya has gone there. So, I want to, because we are talking in Bharat, and we are talking about relating India's scientific tradition to what we do in the world now, I want to tell you a story that many of you will not know, of how our studying the sky from space came along. It has a very interesting Indian connection. Why? Story starts from the fact that we discovered about 1860s, 1870s, that you can take spectra. By a spectrograph, you can take light that comes from anything and break it up into its colors. It's called a spectrum. Here's a spectrum of the sun. If you can, it's a very high resolution spectrum, so it has been wrapped around like that because it's very long. And you can see there's so much information in a current spectrum of the sun. There are all these little lines that tell you these absorption lines are characteristic of certain chemicals. You know that things get different colors because there are absorption lines and emission lines, spectral lines associated with certain chemical components. And so here is the spectrum of the sun. This is so much information in there. It tells you about what kind of composition there is in different layers of the sun. In fact, you probably know that helium as an element was discovered in the spectrum of the sun. That's why it's called helium, from an experiment conducted in Andhra Pradesh. So the spectrum of the sun, when stellar spectra were being studied in the 1870s, 1880s for the first time, people were trying to see whether the spectra could be used to study the stars and to figure out what the stars are, because nobody knew at that time what is the source of energy from stars, and they were trying to classify stars, etc. There was a big effort underway at Harvard University to study, to classify stars according to their nature by having a large basis of stellar spectra, but they could not make any headway. The person who came to the rescue was Meghnad Saha. Meghnad Saha came up with what we call the Saha ionization equation, in which he applied quantum mechanics to the knowledge of atomic physics at that time, combined the Boltzmann equation, the atomic physics, and the quantum mechanics to come up with a whole idea of how lines are produced in the spectrum by different elements in their different ionization states. Okay, you take electrons in their various energy orbits in the atom or in the molecule, and they would be governed by certain laws of quantum mechanics. In classical mechanics, it couldn't have been found. Saha sorted it out. In the 1920s, Saha's ionization equation solved it. And then in Harvard, this whole tradition of gathering the spectra of stars, they realized that there's somebody in India who's invented this theory. They started applying it to it, and it was all sorted. They understood exactly how the stellar spectra actually told you what different kinds of stars there are. What is the relation between the temperature of a star and its chemical composition and the kind of spectra it gives. The first famous PhD, the first woman to get a PhD from Harvard University, Cecilia Payne-Gaposchkin, applied Meghnad Saha's equation to these stars and came up with this idea. Then Saha was invited to Harvard. Saha made that trip in the 1930s and met the famous Harvard astronomers, including somebody called Harlow Shapley. Shapley was then the head of astronomy, and he met Cecilia Payne-Gaposchkin. Cecilia Payne had already become a faculty member at Harvard at that time, first science professor, who's a woman. And then he had a wonderful discussion with the Americans. Now, why am I telling you all this? 1955, Meghnad Saha passes away suddenly. You know, he was a member of parliament, and he passes away suddenly. And in his obituary, various people start writing about various aspects of his life. And Meghnad Saha had a very colorful life. He did many things, as you know. He fought for Dalit rights. He became a member of parliament. He got involved in rivers and Damodar Valley project, member of planning commission, all kinds of things he had done. He'd built his own accelerator in Calcutta. Harlow Shapley talked about Saha's visit to Harvard in this particular obituary, which came out after he died. And in this obituary, Shapley writes, as Saha came to talk to us in the 1930s, he said, look, a lot of the stellar spectra can be solved if we can study the ultraviolet part of the spectra. And the ultraviolet part, this is a man who's realized that in 1930, that much of the information about the star is in the ultraviolet and we don't see it from the Earth. So he started talking in America about what would happen if we could build an observatory, a telescope, that we can send out in the stratosphere, above the atmosphere. A stratospheric observatory. Shapley writes in the obituary, it was entirely Meghnad Saha's idea. That idea later got fructified before India could do anything. That proposal went to NASA, and this entire line of effort to get a telescope in space from the 1970s finally led to the Hubble Space Telescope being launched in 1990. And I've met Martin Schwarzschild, who was the main project director of 1990. Everybody acknowledges that the first person to talk about an ultraviolet telescope in space was Meghnad Saha. India's own ultraviolet telescope, AstroSat, came in 2015. And the second one is going now to the sun, Aditya L1. There are many parts of the electromagnetic spectrum that give you all kinds of information that you cannot get from the Earth. I talked about ultraviolet, I'll come back to it at the end. But other parts, just outside the part that we see, is the infrared. That is also stopped by the atmosphere because it's stopped by water. Atmosphere is full of water. Water molecules absorb infrared. We have some infrared telescopes on the Earth. They are sent to the top of the very highest mountains where there is little water on top. The best infrared telescope is Antarctica. You probably don't know that the driest place on Earth is Antarctica. And Antarctica, because all the water is in the ice. And so very dry. And if there is no water in the atmosphere, you can see things in the infrared. But the best space, of course, is to go to space. The observatory that followed the Hubble Space Telescope, which is now up and causing a havoc out there, is the James Webb Space Telescope. And I hope ISRO wakes up and sends something like that later on. Has been producing amazing, amazing pictures, and these are all in the infrared. Hubble Space Telescope worked in the ultraviolet. James Webb Space Telescope works in the infrared, a different part of the spectrum, and is giving us all these various kinds of, as you must be reading, it has found the farthest objects in the universe, James Webb Space Telescope has found, and is also looking at things that we have seen normally with normal telescopes, and is finding all kinds of things happening in these systems that we've never known before. Another very important part of the spectrum is X-rays. We all know X-rays because we walk into a hospital and they X-ray us and give you a picture of the bones, etc. And that is because X-rays pass through tissue. Building X-ray telescopes is very difficult because you build a mirror and the X-rays pass through them, right? Because they pass through you. So it had to wait till 1970s. And then people realized the only way you can reflect X-rays to form images is if the X-rays actually land on the surface of the mirror at a very small angle. If they land like they normally do at a very large angle, then it will go right through. And that is because the particle spacing on the surface of a solid is nanometers. That is the wavelength of X-rays. And so they actually see as if you are throwing a ball on a wall where you have a railing which is bigger than the size of the ball. How do you get that wall to reflect that ball back to you? You have to do it from the side so that the railing looks like it is, the spacing between the railing is small. So once that was done, then people could build X-ray mirrors. And also, they had to be sent to space because the atmosphere stops X-rays. As soon as we did that, we realized, oh my goodness, there's so much out there that we didn't know. Everything that we are looking at actually looks very different in the X-rays. And here, India has gotten into this. I'll give you an example. Look at this. Here is a cluster of galaxies that I have studied in my life quite a bit. On the left-hand side is a cluster of galaxies, Abell 3528. It's part of the Shapley supercluster that I discovered, named after Shapley, long time ago when I was a PhD student. Here is a picture taken by a very big telescope. Isn't it boring? What do you see? Some spots of light, those are galaxies. And I know there's a cluster of galaxies here because there are 300 galaxies here. You can study them, I studied them. On the right-hand side is an X-ray telescope picture from space, taken of the same thing, same scale, same size. Look at how much you see on the right. All this stuff. That galaxy is that galaxy. That galaxy is that galaxy. But what is there in between the galaxies? It is hydrogen gas whose temperature is 10 to the power 7 degrees. 1 crore degree temperature. This was discovered in the 1980s. That is what is in between the galaxies. What makes it so hot? The galaxies are moving very fast. And the gas that's left over from when the galaxies are formed get hot because there's so much kinetic energy in there. And when things are that hot, they emit X-rays. They don't emit any light. So once we know that, we can get so much information about these clusters. We know how fast the galaxies are moving. We know what is in there. We know the amount of matter that there is in the clusters. Lots of information that we can get by looking at things in the X-rays. And it's all, you will agree, it's far more colorful and far more informative. This picture that my student produced got into one of the European Space Agency calendars for many years because it was so beautiful. Similarly, you can look at things like that. I mean, the Crab Nebula looks boring, but there is so much information there, and you can monitor them, and in real time, day after day after day, you can find a supernova remnant changing, things like that. So everything has to be done from space. I'll give you one example from my own work. Here's a galaxy I've worked with for many, many years, maybe 25 years now, called Centaurus A. It's a nearby galaxy. And this is a picture taken by a telescope, small telescope on Earth. You will agree it looks very interesting. There's a little dust lane in the middle, but these are all stars. And when you see stars, they will be a few thousand degrees hot. That is why they emit normal light. Our sun is 6,000 degrees hot, and it emits yellow light. Something that's about 20,000 degrees hot will emit blue light. Something that's 2,000 degrees hot will emit red light. You go below 2, it is not emitting light at all. It's emitting radio waves. If you go above 20,000, it's going to be ultraviolet X-rays and things like that, right? So these are all normal stars. Now, let me tell you that in this picture, there are a lakh black holes. You won't see them. But how would you see them? Because black holes are extreme objects that pull matter from nearby stars, and as the matter falls onto the black hole, they get very hot, 10 to the power 7 degrees, they emit X-rays. So I was involved when I worked at Harvard and NASA to build this X-ray telescope that went up in space in 1999, named after Chandrasekhar, called Chandra, which had the mirror I'm talking about, the kind of mirror where you have the light come at grazing incidents and they form nice images. Okay, and I'll show you the picture of the same galaxy that we have now formed out of 20 years of studying the same galaxy year after year after year and building together an image. And that's what it looks like. Now, each point in here is a black hole. It's not a black hole. You're not seeing the black hole. You're seeing the stuff that's falling onto the black hole and becoming very hot. It is 10 to the power, anything in this picture is 10 to the power 7 degrees hot. 10 million degrees hot, 1 crore degrees hot. Anything in this picture, same galaxy is only 10,000 degrees hot, or 6,000 degrees hot, or 5,000 degrees hot. So you see what I mean by detective. You get different information. You put the two together, then you say, this galaxy has stars, it has black holes, it's got all kinds of things, and then you start making a whole picture about how did the galaxy get together, how do the stars interact with the rest of the other stars, of the compact stars, how much gas is in there, etc., etc., etc. Another thing I work on, which was introduced when I was introduced, I was told, is superclusters of galaxies, which is the largest structures in the universe, which are, galaxies. We live in a galaxy, the Milky Way, Akashganga, but there are galaxies that are connected with other galaxies in clusters, and then clusters form superclusters. And we ask the question, how big can these structures get? We don't know the answer yet. We are discovering larger and larger structures. We have discovered structures that have 30, 40, 50 galaxies altogether. And now we are discovering things that are hundreds of thousands of galaxies. And these are called superclusters. While I was doing my PhD, I found what is known as the Shapley supercluster. This is actually a map from Wikipedia, you can see now. People have started mapping all these different structures of galaxies in the universe. The Shapley is in there, which is something I discovered during my, my time as a student. While I was in IUCAA in the last few years, and people, I don't know if many of you came to the talk I gave to the Vigyan Parishad about 6 years ago in Mumbai, where I was fresh out of, after discovering this thing called the Saraswati supercluster, which went to the front page of the papers. It even made it to the last question of the Kaun Marega Crorepati at that time with Amitabh Bachchan. Saraswati supercluster. If you look at the Saraswati supercluster, which is another thing we discovered in our group in IUCAA, it's a very, very large structure of galaxies, about 50,000 galaxies in there, which are very long strings of galaxies. We have now started studying them in the X-rays and in the ultraviolet and in the radio. And we are finding clues as to how these large structures form and how big they can be. One of the latest results from that is this, where you can see that on the left again is a whole, with all this light you might not be able to see, but you can see that in the middle of these supercluster of galaxies, you've got lots and lots of, you can see there are filaments of galaxies. So each point in here is a galaxy. You look in the X-ray with the Chandra X-ray telescope, and you start looking at what's in between the galaxies. All this stuff, all the red stuff is in here. It is telling us that actually in between the supercluster there are large string-like or avenue-like like structures along which these galaxies are moving, and as a result they are interacting with the gas in between the galaxies, heating them up to very high temperatures. And this is the first clue we're getting as to how structures form in the universe. We're asking questions, very important questions. Like, the universe started with a very uniform universe. How is there so much structure in this room? There are clumps in this room. In the universe, galaxies, stars. And so this is the first kinds of clue that are emerging of how structures form. Do they form very large scales, or do they form very small scales and things like that? So we're bringing in information from different parts of the spectrum. Finally, I won't take much time to talk about, I'm going to go back to ultraviolet. Ultraviolet is very important because it's just beyond our vision. We can see up to about 400 nanometers, 4,000 angstroms in wavelength, and anything bluewards of that becomes ultraviolet. Stars that are slightly hotter than about 20,000 degrees, newborn stars are always hotter than 20,000 degrees, suddenly become visible mostly in the ultraviolet. So ultraviolet, the wavelength is about 10 to 400 nanometers, becomes very important to study how stars form. and also how stars form early on in the universe and also around us now. We want to know how the sun formed. We want to know how the stars around us formed, how the galaxy formed. Crucial things. Young stars are 50,000 degrees, 100,000 degrees hot. Much of the light they emit is in the ultraviolet. So this is why one of the first astronomical facilities that India built during Professor Kasturirangan, Dr. Kasturirangan's time. I remember Dr. Kasturirangan was then chief of ISRO, and in his office meeting, because he was the first astronomer also to become chief of ISRO, he called a meeting of all of us. I represented IUCAA at that time, 96. And he said, we have to build a space telescope. It became AstroSat, where there were 5 space telescopes, X-ray telescopes, ultraviolet telescopes. And the conversation was about, we have to see outside our visible range and see what we can get. And we have to be a world-leading telescope. AstroSat was then started in 96. It finally flew in 2015. Things take a long time in the Indian system. But now we've learned how to do this. And AstroSat was also the first thing ISRO built in which outside ISRO, other institutes took part in building things. So IUCAA, for example, built instruments. IIA in Bangalore built instruments. PRL in Ahmedabad built instruments. And all of them got together and built different parts. TIFR in Mumbai played a very important role in building the X-ray instruments. And this was the first time ever that 5 telescopes went on the same satellite. And with this, it's still running. With this, you can point to a star or a galaxy and observe with 5 telescopes at the same time, X-rays, ultraviolet, everything together. And AstroSat has become amazing. It has shown us lots of things that we've never seen before, and is now discovering very, very nice objects very far away in the early universe, a lot. And that gave us the courage to build Aditya. Because we knew that in order to study the sun, we need ultraviolet. That's where the sun is most active. And other agencies like in the US and in Europe and in Japan, they had built sun studying instruments, but they were not looking at the sun, not just the sun, but its relationship with the corona, because we know that everything that happens on the sun actually affects the corona, and it emits energetic particles that come and affects the earth as well. So we're looking at the relation between the sun, the corona, and the earth. And this is where Aditya is. Aditya is not going to go around the earth like the Hubble Space Telescope does. It is, as you know, going to go to a place called the first Lagrangian point, which is 1% of the distance from here to the sun. The great thing about the first Lagrangian point is that that's a place where if you place something, then the gravitational force of the earth and the sun balance out, and it can be parked there. It stays stationary. Actually, it's not going to stay stationary. It's going to have a little orbit around it, like that, okay? And it's almost there. It's about a month away. And I'll end my talk now with the picture that I showed you before, just to show what it's sending us back. These are pictures of the sun in different parts of the ultraviolet spectrum, between 200 to 400 nanometers. There are filters that take, say, 200 to 220, 220 to 240, 240, etc., right? And you can see these are slices in wavelength. And you can see how the sun, at the same time, looks different. There are storms going on the sun. And you can see them only in some parts of the ultraviolet at particular wavelengths. That is extremely important for us to know. And then, at the same time, you're looking at the same sun from the earth, and you can see the sunspots, etc., and you can see the difference between the two, and it's already will give us a lot of information. This is just the first experiment. It hasn't even reached there. This is just the instruments are being tested now. And various data is coming back. We're looking at the data. But ISRO said, why don't we publish the first pictures? A PR exercise offer. I mean, I can't get much science out of this because the instruments are not calibrated yet. But great. I mean, this is just shows what we can do. 5.5 years of this is waiting for us. for me, when this picture came out, I said, wow, the sun is in the middle. I didn't know, the camera could have been slightly misaligned and the sun would have been outside it. So that kind of joy comes to the person, the team who has made this for 7 years. And it is giving you the first pictures. And he said, oh, gosh, it's working. It's working. The sun is there. So that's it. So this is only the beginning. You will hear more about this. But I think what I wanted to do today is to come to you and say that the reason I'm excited about astrophysics is that it's a subject that's beginning off. It's just like when, say, particle physics was in 1900 when the electron had just been discovered. We've just found a way of finding information that is so much more than the information we were dealing with till 50 years ago. And this is where young people and parents of young people should seriously think about how this is going to change our way of thinking about the universe. And this is where a lot of energy and finances need to go in sustaining sciences like this. I'll stop here and take questions. Thank you very much. I hope people have questions. Somebody will take mics to them. I don't know how much time we have. 10 minutes or so? Okay. 5-10 minutes.
Good noon, sir. Myself, Sanjay Devulgaonkar from Marathi Vigyan Parishad, Navin Nanded. First of all, I tribute to all you astronomers for finding out this combustion theory of sun. My question is that, sir, simply if we are taking a hydrogen atom and we are imparting some energy, we find out different energy bands like Lyman, Blammer, Paschen. So when we are sending some radiations, there are different spheres in atmosphere and there are different climatic conditions in spheres. So whether that is affecting those radiations and we are not getting the true pictures of the sun?
Very good question, absolutely. So, this is a good example. This is a picture of the sun, a spectrum of the sun taken through the atmosphere. Okay? And a lot of these bands that you see and absorption happening within the sun, because in the sun, the energy is coming from inside the sun and it comes out through different layers which are cooler and cooler and cooler and cooler. Inside is 20 million degrees, outside is 6,000 degrees, and cooler, 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 and so things get absorbed. And we know the conditions of the various elements, not just hydrogen. The sun is made up of much more than hydrogen. You get a lot of elements from the periodic table, up to carbon, oxygen. They are there in various layers of the sun. And so we know the chemical composition of these elements, and we know at what conditions they are in, pressure, temperature, etc. Many of the lines you see are actually from our own atmosphere. And so any astronomical study, even from the first year when students go in to do research in astronomy, they have to learn how to take out the effects of the atmosphere. You very rightly say it is coming through the atmosphere blurs the image, but also adds things to it. There are so many things that are in the atmosphere. Not just atmosphere, just look at observatories and telescopes that are in cities. You have the street lights. The street lights have mercury in it or sodium in it. It's adding all that, right? And so the way we deal with it, so look at the working telescopes we have here. Ayuka's telescope is in Giravali, and there is so big human settlements there. What we try to do is to design filters to filter out the man-made kinds of information that comes in the spectrum. We have to correct for whatever we know about the atmosphere, its compositions in various parts, etc. And only then can we actually publish numbers. So there is a huge part of a practicing astronomer's life is to know and to learn how to deal with correcting for the atmosphere, both the composition of the atmosphere and also the physical conditions of the atmosphere. So that is actually a huge part of our work. And often you will find that we discover new things about the atmosphere by doing this. Yeah. So we have found many, many different atmospheric phenomena, molecules and ions that are in the atmosphere that people didn't know of before by studying astronomical objects and in great detail. So that's a very important part of our work. Anybody else? Yes. Can somebody give me the mic? Oops, sorry. There's somebody here. If you have another mic, if you can go there. Yes, please go ahead. Thank you.
Hello, Sunanda Karandikar from Mumbai.
Thank you.
I want to ask you about the last picture which you had, no? There were so many images of sun. There were 2 images only green which were there, which was at the shown aside, similar, last. This. There are those 2 green which you have shown side by, that way 2 green, and others are different colors.
Yeah.
Can you just elaborate on
Actually,
that?
I'll tell you one thing. I mean, I should have explained. It's a bit of a cheat in there. These are not real colors. These are not real colors. These are all false colors. These are colors that are put in there to bring out various effects. The reason being that actually, if I'm an astronomer, I don't use color cameras. Color cameras are impossible to use in a scientific setting. Color cameras, color sensors are only there to give you a nice aesthetic effect if you're taking a picture with your phone. But if you want to do anything scientific where you want to measure something, they are impossible to measure light with. So people don't. But then you tell me, you're showing me so many pictures in astronomy, they're all colored. Color is used in a creative way to bring out different effects. For example, in here, these colors are used only to look at the difference between this and this and this and this, etc. Right? And in general, colors are used to tell you that blue, for example, is higher energy than red or pink, that kind of stuff. So it gives you some sense. But these are not real colors. And so it is not that the sun is actually blue. All of this is blue. It's ultraviolet. From 200 to 400 nanometers, it's all ultraviolet. So these are actually all ultraviolet pictures of the sun. And blue won't mean anything because it is not, you won't see it with your eye. Our eye sensitivity stops at 400 nanometers. So it's false color, it's only there to bring out things.
Okay, sir, but how do you explain about these? The different things are there, then what do they
So this is something, of course, we have to understand now. As I said, this picture just came yesterday night.
Yeah, I know.
And in the
I
morning,
know.
I saw this on Twitter, I put it up. I haven't seen it very well. But what's happening is, as you can see, all this stuff, right? Those are all magnetic storms. We know that. We've seen this before. We've seen this before because there have been other solar observatories before, but not full disk observatories. All this stuff, these are, something like this is the size of the Earth. And these are magnetic storms going on right now. So the next year, the sun is going to reach its maximum activity. It has an 11-year activity. So it's now pretty active. And yes, now 2025 is the, early 25 is the maximum. So as you go up, you will find that activity, and when more activity happens, that means more storms happen on the surface of the sun. Now, what do you mean by storm? It is not like our cyclones. These are magnetic storms because a very strong magnetic field on the surface of the sun. And so charged particles are moving along the magnetic fields from one part to another, right? And they create a lot of
disturbance.
Right, exactly. And so these are, and that's why it's also in the ultraviolet and X-rays, because these are very high energy light that is created. You know that any physicist would know that there are various kinds of radiations that are produced by charged particles that travel along magnetic fields. These can be Compton radiation, this can be Bremsstrahlung, this can be all kinds of things. So, a synchrotron radiation, things like that.
Yes, yes.
And so these are different kinds of radiation where charged particles move along magnetic fields. And so such things are happening, but why is it happening at certain energies and not at others? And these are very interesting things that we need to understand. It tells us something about the charged particles and about the magnetic fields. And there are whole bunches of people who do modeling to find out what you get to know. And many of these charged particles that you are seeing in these will end up on the Earth, right? Because they come to us and they create similar effects in the Earth's atmosphere. Aurora borealis, for example, are charged particles from the sun that comes and gets captured in the Earth's magnetic field. Then they start moving, stuff like that. But that's at a much lower energy scale. These are very, very violent phenomena.
Thank you, sir.
Thanks. There was some question on this side. Yes, thanks. Huh? Good. SOHO and Solar B are the two observatories that were launched. And in fact, I was involved in Solar B because I actually worked at the University of Birmingham for 15 years. And in my basement, the Solar B camera was built. So I know it very well. But that was 20 years ago. Those were launched 20 years ago. And those are there. In fact, it's just where Aditya is going. In L1, SOHO is sitting there. And they are 20 years old technology. And just see how much has changed in 20 years in this kind of technology. In sensor technology, computer technology. When SOHO went up, when SOHO was designed in the 1990s, computers didn't have kilobytes. Right? And now we can make sensors that can get gigabytes of data and send them back by the telemetry that we have. SOHO was not even designed to do that because there was no way of sending that kind of data to us. So their design was not trying to, that's why I'm saying not trying to capture the whole image of the sun. They would have, where would they store all those bytes? Right? So it is a very small field of view. So what SOHO does is actually scans at a very slow rate different parts of the sun and sends in little bits of data at a time. And also their resolution was not very good because their sensors didn't have resolution. This kind of resolution no telescope has. Right? So now we have higher resolution, higher data rates, and that will give us a lot more information. It is not about general kind of blurred effects. We're looking at, actually we'll be able to find places on the sun and find out characteristics of each place on the sun much better. So this is far more advanced.
I have a comment and a question.
Yes.
I first heard of you in connection with those fine hair-like size fibers which were used to make an X-ray detector for seeing black holes.
Seeing what, sorry?
Black hole X-ray emission. So that's the first time I heard about you. And after that, then when you were working in IUCAA, I had heard about you.
Yes.
See what is happening in astronomy. I mean, when a student is interested in science generally in school, they have a whole variety of sciences they could pursue. Supposing they have to look towards astronomy. Astronomy is getting more and more expensive because of the kind of instrumentation that is required. And it takes about 10-20 years to get a new line of instrumentation, which will then produce new results. So if you time it right, you might get into it. And there is a whole hierarchy of selection process. So maybe in whole of Navi Mumbai, if you produce one astronomy person in 5 or 10 years, I think that would be a good guess. So, of course, on the internet, we can see the whole information of astronomy within a few minutes or a few hours or a few days of all these discoveries. So there is a lot of data people can see and work with. So you have a contrast now. You can't get into the top institutions to actually work on these things, but you can have all those informations readily available for you. So how would you guide people in this scenario?
Is your question or comment related to that? Because I'll tell you. So, there's an information explosion everywhere. You have a very good point there. But there is one thing. Astronomy is not just a data science. It is producing huge amount of data. And data is out there. And one of the great things that astronomers have done, we've set standards in this, that we make our data public. This is internationally done. In fact, I was in the first negotiation with ISRO about AstroSat when we proposed ISRO, and ISRO said, so how much are we going to sell the data for? And I said, no, we're not selling data. AstroSat data is not, astronomical data is not sold. It is made public. And as a result, what has happened, because of the openness of the data and availability of the data, a lot more discoveries happen because anybody can get into it. My first year student, undergraduate, can actually do a project on that data. What astronomy is doing, it's producing a lot of data. And there have been efforts, global, India led the virtual observatory project, Ajit Kembabhi at Ayuka and the work with persistent systems in harnessing data tools such that we can actually work with the data. Even that is not enough. Not enough because I showed you the logarithmic space of the amount of potential data that you can get. What is important in science is not, serendipity is important in science. Importance in science in the sense people get discoveries by starting to do things and suddenly they stumble upon things. But that is not the only thing. Experiments have to be cleverly designed, instruments have to be cleverly designed to do new things that will bring new kinds of data. And there is so much potential now to do that kind of thing now. I agree that astronomical data, astronomical instruments and telescopes are getting more and more expensive. But I want to put that in perspective. Chandrayaan cost 600 crores. That is 1/5 the price of a Boeing aircraft. Right? People kept saying, oh, can India afford Chandrayaan? It's nothing. What is 600 crores in terms of, 5 Chandrayaans make a Boeing aircraft. So but that's not the most expensive thing. I mean, you're looking at India contributing to the 30-meter telescope or to LIGO. These are 3,000 crore projects. Now, 3,000 crores, well, not 3,000, 2,600 crores will be spent if the money comes on the LIGO project in Maharashtra, in Hingoli, where it will be set. Why are we spending this money? Remember, all 2,600 crores will go into the Indian economy. Everything will be built by Indian companies. It will create jobs, it will give new technologies, new challenges to Indian companies. So it's all connected. I think spending the money in building new facilities that are cutting-edge facilities not only boosts high-tech economy, it also gives a lot of lateral benefits into this research. I mean, the fact that the digital camera came out of astronomical research, and now everybody has it in their pocket, right? It was created because, people wanted to find a camera that will be taken up by a space telescope and that will not have to be taken to a chemical shop to be developed, right? So similarly, there's so much, I hope you can actually, it's very easy to go on the web and look at collateral things that are coming out of sensor research of building astronomical instruments. I have a friend in Glasgow. Glasgow has built the entire LIGO gravitational wave technology, the vibration-free technology where the mirrors are suspended and such that the earthquakes don't shake the mirrors. And it's to the precise level such that very little vibration even won't happen even if the ground shakes, the building shakes. He has spun off a company now and is building instruments for people who are eye surgeons, who are operating on your eye. And so, for example, that finger that is operating on your eye does not shake, right? And he's actually building and marketing these instruments. Where is astronomy and where is eye surgery? So that's how science works. We have to push technology. I've just shown you a way of pushing technology, pushing the boundaries of knowledge. It doesn't matter whether it's astronomy or not. Astronomy is good because it produces nice pictures, kids get very excited. But what happens after that? It takes them into fantastic areas, they learn skills. Somebody mentioned this morning, 13 PhD students that I have guided in my life, and of course another 20 I've co-guided. Of those 13 PhD students I've guided in my life, 7 are working in financial industries or computing industries. I taught them computing. I taught them data analysis, right? People do all kinds of things. They're contributing to humanity. Anyway, thanks. Any other question?